Welcome to Spring LIB.
Assume we have a pendulum consisting of a cord of length L and a mass m attached to it. If this pendulum is allowed to swing and is then interrupted at its lowest point by a peg, the pendulum will transcribe a circle in its motion. How do we know what the minimum possible speed at the bottom of its motion for the pendulum would be to be able to pass through the entire circle? Well, let's look at what the conservation of energy tells us. Firstly, at the bottom of the circle, this is the initial point of reference. We know U, which is the potential energy, mgh, is 0. So the bottom of the circle is taken to be at a height 0. And the kinetic energy, K, is equal to a half mvi squared. And this is what we are trying to find, vi, the velocity as the pendulum begins to make its circular trajectory. At the top, for our final reference position, we know U is equal to mgh, and h in this case is just L minus d. So at this point, at the top of the circle, what is the kinetic energy at this point? K is equal to a half mv squared f, the final velocity. Well, we know that this is centripetal motion, so the kinetic energy is mg times r. This is due to the fact that the centripetal acceleration g is just v squared divided by r. And r, being the radius of the circle, is just L minus d. So that's a half mg into L minus d. Now, the conservation of energy tells us that the energy before has to be the mechanical energy after. So a half mvi squared is equal to 2 mg into L minus d plus a half mg into L minus d. So the sum of the kinetic energy and potential energy before, or at the bottom of the circle, has to give us the sum of the potential and kinetic energies at the top of the circle. So if we do a bit of rearranging, we find vi to be the square root of 5 times gravitational acceleration g into the radius of the circle, L minus d. Okay, so the minimum velocity or the minimum speed of the pendulum at its lowest point, vi, is square root 5g into L minus d. But what is the minimum angle theta? Well, the minimum angle theta will tell us the angle at which the pendulum needs to be released so that the pendulum can pass through the entire circle. Again, we can use the conservation of energy. So the initial potential energy plus the initial kinetic energy, is equal to the final potential energy plus the final kinetic energy. So The pendulum starts at a height h, which is unknown. It has zero kinetic energy as it starts from rest. Its final potential energy is zero as it reaches the bottom of the loop, and at that point the kinetic energy is a half m times the square of the velocity that we found earlier. So that's just 5g into L minus d. The velocity is the square root of that. So v squared is just everything under the square root sign. But what is h? Well, with a little bit of trigonometry, you can see that h is actually L into 1 minus cos theta. And this is a half m into 5g L minus d. Well, now this looks a lot more promising. So if we rearrange this further, we see 1 minus cos theta is equal to 5 over 2, 1 minus d over L. And lastly, with a bit more mathematics, we see that this gives theta as the arc cos of 5d divided by 2L minus 3 over 2. So this is the minimum angle at which the pendulum has to be released in order that it makes the sufficient velocity to complete the circle.